Okay, this is an area we call stoichiometry, and stoichiometry is looking at the either mole relationship or mass relationship between reactants and products in a chemical equation. Okay, so we call this stoichiometry. And actually it's called reaction stoichiometry because it is chemical reactions we're looking at. And it's basically looking at mole and mass relationships. In chemical reactions. First thing you have to do before you do anything is write out the reaction if it's not written out. So this reaction is written out. Next thing you have to do is you have to balance it. If you remember our balancing technique we did, and I'll just show it to you. Some of you can do it by sight, but I'm just going to write down each element and then write down how many I have. Subscripts will tell me on each side, and so that way I can make a direct comparison between. Alright, so I'm going to go, I'm going to leave oxygen to the very end because it's in two spots on the right side, and so I do not want to attack an element that's in multiple locations on the side. First thing I'll do is I'll look at balancing out my carbons. So I've got 5 carbons here. And so I'm going to put a 5 in this, front of CO2. And what that does is it changes this carbon here to 5. So I have 5s. But it also changes my oxygen to the big 10 in the CO2, and then I've got 1 extra in H2O. So I have a total of 11 on the right side of the oxygen. The next thing I'm going to do is I'm going to balance my hydrogen. If you notice on the left side I have 12. On the right side I have 2. So I'm going to put a coefficient in front. And when I put a coefficient in front, that makes it 12 hydrogen. So 6 times 2 is 12. So I've got 12. And so my carbons and hydrogens match up. Now I just recount my oxygens. I've got 10 oxygens in CO2, and I've got 6 oxygens in H2O, which is a total of 16. So I've got 16 on the right side. On the left side, I just have to put an 8 in front of O2, and that makes it 2 times 8 is 16. So now they're balanced out. So now what I can do is I can do what's called a mole relationship. That's the first one I'm going to do when talking about balancing or talking about how to set up these reactions in which to solve for a particular amount of moles or grams on one or the other sides. So what we're going to do, this is called a mole to mole problem. We've got moles of oxygen we want to know. So we want to know moles of oxygen. I just, down below each equation, I'll just represent moles, and then that's an easy way to kind of show that relationship. And then pentane is C5H12. So I know how much I have of that. I have 4.2 moles. So that's what I have of pentane. So on this one, all I'm doing is looking at the relationship between C5H12 and oxygen. And I can see that that relationship is a 1 to 8. That means I've got 1 of the C5H12 for every 8 oxygens. So I need a lot of oxygens for this reaction to happen in relationship to the C5H12. So what I'm going to do is I need to transfer from moles of C5H12 to moles of oxygen, because that's what I want to find. I want to find the moles of oxygen that it requires to have this reaction take place. to get rid of all the 4.2. So, kind of like a recipe. How much do I need of one reactant versus the other for this reaction to go to completion? So down here I'll put moles of C5H12. And up above I'll put moles of what I'm trying to find. Moles of O2. Moles, as you find out on every single one of these problems, you're going to do this relationship that is that I'm writing out right now with moles of C5H12 and moles of O2. You always have to do, it's kind of like a translator. It's a way in which you to move from one element to another element successfully. So in front of moles of C5H12, I'm going to put the number that's it's the coefficient in front of C5H12, which is 1. And in front of oxygen, I'm going to put 8. So now, if I want to find the moles of oxygen, I just go ahead and multiply the 8 times the 4.2. My units cancel out. So just like conversions, those units cancel out as you go. And when you get an answer, I'm going to pay attention to significant digits. I have 2 in my measurement. So what I'm going to have is I'm going to have 34 moles of oxygen in my final product, or my reactant that I'm making. So that's how you do what's called a mole to mole problem. Like if you go from moles of A to moles of B, which is a different type of reactant or product.